Okay, so we will move on to the next numerical. Okay, so this is also so that you write down the equation. Okay, now we have to derive the expression for k for a triangular channel with side slope is given 2 horizontal is to 1 vertical, and this is your given expression, that is k is equal to, we have to derive this. Okay, 1.169 y to the power 8 by 3 divided by n. Okay, so we need to derive this for a triangular channel. K is equal to 1.169 y to the power 8 by 3 to the power n. So first you write down the equation. Okay, okay. So this is again we have considered the triangular channel. Okay, here z is equal to 2. Okay. So one vertical is to 2 horizontal. So z is equal to 2. In this case, okay, z is equal to 2, and then y we have considered y. Okay, depth of flow. So again we are going to use the area equation, half into base into altitude. So this is half. Then definitely the top width will be twice zy and multiplied by the depth of flow. Okay. So again it will be area equal to zy square, and z is 2 in this case, so twice y square. Okay. So then we move on to weighted perimeter, this side and this side. Okay, so it will be same, so multiplied by twice root over this side square and this y square. Okay, we consider this triangle. We consider this triangle. This side is equal to root over this side square and this y square. Okay, here this y square and y square is there. We can bring it out. So 2 to the 4 plus 1, it's root 5. Okay, if you solve, you will get twice y root 5. Okay, So now we are using the k expression that you have already discussed. Okay, k is equal to a r to the power 2 by 3 n. Okay, k is nothing but q root over sb, if you remember. Okay, q, that is our discharge, root over sb. So this is your Manning's equation. V equal to 1 by n r to the power 2 by 3 sb to the power half. Okay, so velocity, in place of velocity we can write discharge by area is equal to 1 by n r to the power 2 by 3 sb to the power half. Okay, so sb you bring it this side, q root over sb, and area you bring it in the right hand side. So it will be area multiplied by r to the power 2 by 3 divided by n. Okay, this is the equation, and this q root over sb is nothing but your k. Okay, so we use the k expression for k here, and then we substitute these values. Area we have already calculated. We substitute the expression for area. R is nothing but a by p. Okay, okay, so you substitute all the expression in this equation and see you are getting the same equation or not. I mean this equation. Okay, k is equal to this. You try to solve. Here in this equation you substitute all the parameters like area, and in place of r you substitute a by p. Okay, area and perimeter we have already derived the expression. Okay, so perimeter is nothing but twice y root over 5. Area is twice y square multiplied by area is twice y square divided by twice y root over 5, and then we have to the power 2 by 3 divided by n. Okay, to solve this expression and see you are getting this value or not. Okay, over, you are getting, okay, okay, okay. It's very easy, okay. First, you have to derive for area, then you have to go for perimeter, weighted perimeter, then you directly use the expression for K. So we have two expression, one related to Mannings and one related to Sages. As in the given expression, what we need to derive, we have small n, so that is why we have used Manning's equation. Okay, and you directly substitute these values, what we have already derived, that area and perimeter, and if you further simplify, you will get this expression. Okay, okay. So next topic, okay. Next topic is computation of hydraulic exponent capital N. Okay, this is our next topic. We are going to derive an expression for capital N. Okay, we are going to derive an expression for capital N. N is nothing but your hydraulic exponent. Okay? So in the derivation, we can also use Sage's equation and we can also use Manning's equation. Okay? So if we use Sage's equation, that expression will be a little bit different. And if you use Manning's equation, the expression will be little bit different. Okay? So that is why we have two cases in that derivation. One is Sage's equation and one is Manning's equation. Okay? So the first case, we have used Sage's equation. Okay? So you kindly write it down. This is a derivation. It's better if you write it down. Okay? Computation of hydraulic exponent, capital N. First case, when Sage's equation is used. Okay? So then we use the discharge equation, Q equal to area into velocity. Q is equal to area into velocity. So in place of velocity, we have used Sage's equation. As in this case, we have used Sage's equation. Okay. So to calculate velocity, in place of velocity, we have written Sage's equation. Sage's constant multiplied by root over R into SB. Okay. So for K, we already know this expression K is equal to root over, sorry, Q divided by root over bed slope is equal to AC R to the power half. Okay. This is number one. You put equation number one. Okay. Then you write, since A and R is the function of depth Y, the relationship between K and depth. Okay. Next line you write, since the A and R means area and hydraulic radius is a function of depth Y, the relationship, definitely this area and that R is always a function of y. If y varies, your area is also changed. Area is nothing but your depth of flow. Sorry, y is nothing but your depth of flow. If your depth of flow changes, your hydraulic radius as well as your area will change. Okay, so it's always a function of y. The relationship between k and depth can be written as, you write this formula. Okay, This is little bit not visible. So to write k square equal to c dash y to the power n. Okay, k square is equal to c dash y to the power n. Okay, where c dash is nothing but your constant. Okay, and capital N, you can write it's a hydraulic exponent for computation of uniform flow. Okay, where c dash is constant and capital N is hydraulic exponent for computation of uniform flow. Okay, so we'll move on to the next. Then we are going to taking log on both side. Okay, then we are going to take log on both side in this equation. Okay, so if you take log, it will be twice log ek, okay, is equal to log ec dash plus, this is your to the power n, so it will become here n log ey. Okay, so we have taken log in both side. Okay, now in this equation we are going to differentiate. Okay, and it will be with respect to y. So if we differentiate, we are going to differentiate d by dy log ek is equal to, this is constant. Okay, log c dash is also constant, differentiation of constant is 0, and then it's n by twice y. Okay, differentiation n is constant, so we will be differentiating log ey, so it will be 1 by twice y. So this y we bring it here. Okay, this will be something like that. It's a little bit, okay, this is, it's not there. Okay, this is not there. This 2 we bring it here. Okay. So if you differentiate this portion, it will be somewhat like this, n by y. Okay, so as we have 2 here, we bring it in the left hand side, it will be n by twice y. So we can directly write dy dy log ek is equal to n by twice y. This 2 is nothing but this one. Okay, this is 0 because c dash is a constant. If we differentiate log c dash, it will be 0. Okay, so differentiating of this is nothing but n by y, and because of the 2 we bring it here in right hand side, it will be n by twice y. So you put equation number 2. Okay, now we are going to take log for equation number 1. Okay, now we have to take log for equation number 1 here. So again this will be dy dy. First we are going to take log. So log ek is equal to, we have c log ac, then we have area, and then we have r to the power square half. Okay, so half will be here, log er. Okay, now again we are differentiating. See what we are going to do, we are going, first we have taken one equation for k, then we have taken another equation for k square equal to c dash y to the power n. So we are going to relate both the equation, that is equation 2 and whatever the equation we are going to get after taking logarithm and differentiation of equation number 1. Okay, then we equate both the equation, because our aim is to find an expression for this capital N that you can see in equation number 2. Okay, so we have to remove this log ek. Okay, so that is why we are not solving this differentiation. What we are going to do, we this log ek we are going to differentiate, sorry, replace by whatever the log ek we are getting in equation number 1. Okay, and our intention is to find an expression for this capital N, that is your hydraulic exponent. Okay, so next again you take log for equation number 1. This is your log. Then again you have to take differentiation with respect to y. Okay, see in the left hand side we are getting again dy by dy log ek. Okay, you can see in the equation number 2 also. Okay, then differentiation of this is again c is constant, so it will be 0. Okay, here area, so definitely differentiation of log ea is 1 by a, but a is not y. Okay, again a is a function of y, so that is why we have to difference again that a with respect to y. Okay, understood? So this is, if it is y, then we can directly write 1 by y. Here in this case we have written, okay, as this is not y, this is area. Okay, but area is a function of y, so that is why we are, when we are differentiating a, so it will be 1 by a, but that a again we have to differentiate with respect to y, because here we have differentiating with respect to y. So this is just simple mathematics. Okay, so plus 1 by twice r, and again this r is a function of y, so it will be dr by dy. Okay, so r is nothing but a by p, area by weighted perimeter, that we all know, and top width dA by dy is our top width. Okay, so here we are replacing dA by dy by top width. Okay, and r we are replacing by area by weighted perimeter. So after replacing r and dy by dA is the top width by a, so this is the expression you are going to get. So this is in the left hand side, this is also we have kept constant. Now we have to differentiate this. Okay, differentiate a by p with respect to y. Okay, so you can consider like this, p to the power minus 1 multiplied by area. Okay, that is nothing but your u into v. If you remember, we have a differentiation equation, u into v, and another one is u by v. Okay, so you can use this u by v also, you can use a into v, u into v, it's up to you. Okay, if you want to use this u into v, first into differentiation, this is nothing but your first into differentiation of second minus second into differentiation of first, that is v, that you all know. Okay, a simple mathematics. So apply here. Okay, apply here, and after you differentiating, this will be your constant. Okay, 1 by twice square will be there, so that is why we have in this term also we have 1 by twice here. Here also we have 1 by twice here. Okay, so you will get this expression after differentiating a by p with respect to y. Okay, so now p by a, Here again we have considered top width. That is why this is T. Then we have R into P. Okay, R into P twice RP minus area. Then this we have P square. In place of R, we have replaced A by P. Okay, and this will be same dP by dy. Okay, the next left hand side will be same P by A. Then R is again replaced by P, A by P. This P will be cancel out twice A. Then here this A and this A will be cancel out, and this P and P square will be cancel out. Okay, so 1 by twice P dP by dy. Okay, so this is why we have T by A here. This PP will be cancel out. We have T by twice A 1 by 2P multiplied by dP by dy. Okay, next this will remain same. This is also remain same. Then we have written A here and also here. Okay, so that we can bring one R here. Okay, we need one R. Okay, that is why if we solve this, we will get twice P because this A will be cancelled out. Okay, so it will be R by twice A. Definitely, if we add this two, we will get 3T by twice A. Okay, minus R by twice A dP by dy. Okay, so twice A is common, so we'll bring it out. Here also we have twice A. Here also we have twice A. So 1 by twice A, we have bring it out 3T minus R dP by dy. So this is our equation 3. Now we have to replace this. Okay, and we have to bring n. So from equation 1, sorry, from equation 2 and 3, we can equate both the equation, and in place of dy log e k, we can substitute n by twice y. Okay, and then we can find the expression for n using Surge's equation. So this 2 will be cancelled out, this 2 will be cancelled out, and then y will be go up, y by a 3t minus r dp by dy. Okay, so students, kindly go through the derivation. If you have any doubts, okay, then we can discuss here. Okay, so ultimately you will get this expression, which is your general expression of hydraulic exponent in an uniform flow using Surge's equation. That is equation number 4. Students, go through the derivation, okay, and see if you have any doubts. Now after the general equation, then you can also see, so when the channel is trapezoidal, then our area equation, top width again, this is your B plus this is ZY. We have already discussed those things, ZY. So it will be B plus twice ZY, top width, weighted perimeter. Okay. Then if you differentiate for weighted perimeter, you will get this expression for trapezoidal channel. And then we can also find an expression for trapezoidal channel using Sage's equation. Okay. Similarly, we can also go for rectangular and triangular. Okay. So see, for triangular, we will get n value for 5. Okay. You can see here. So those things you can do again. Okay. So in the general expression here, area will be depending on what kind of channel it is. Okay. If it is trapezoidal, then in place of area, we have to use the trapezoidal equation, area equation. Okay. Then R is again, it will be area by P, weighted perimeter. So depending on the channel section, we have to substitute the area equation and weighted perimeter equation. and you have to differentiate the weighted perimeter equation with respect to y. Okay, and then you substitute here, you can directly find out the n value. Okay, and this is your nothing but your top width. Okay, so if you talk about triangular channel, you triangular channel, you find out the top width and you substitute here. Okay, find out the r value, you substitute here. Then you differentiate the perimeter, weighted perimeter with respect to y, and whatever the value you are going to get, you substitute here. So after substituting all the values, you can directly find out the n value. So here we are going to end today, and in the next class we will go for derivation of that hydraulic exponent by using Manning's equation. Okay, and you please go through the derivation. Okay, and see if you have any doubts. Then we can discuss in the next class.